Hello, this is Ruiz, and this is my video submission for Dr. Ruiz BME 247 Microfluidics Lab on Chips course. This particular submission is for PBL number 1, which is concerned with the ubiquitous microfluidic phenomenon. For my phenomenon, I have chosen to study surface tension. Now, let me explain what this contraption is and what it does. So first off, it is simply a cantilever suspended over a needle. I don't know if you can see it there. Yeah, you can. And this cantilever is balanced between this basket and a needle on a string or a thread. I use this counterweight to help balance this because obviously the needle cannot balance with the basket. So what we'll do is in a moment I will fill this bowl with water. This bowl is designed to take a sample. In this case it will be water. And then we will submerge the needle slightly under the surface of the water. Then I'll use this droplet here to put drops of water into the basket, and I will count the number of drops it requires for the needle to be pulled out of the water. Now, using Newton's second law, we can back calculate how much force was required to pull the needle out of the water by figuring out the gravitational force of the weight of droplets in this basket. Now I will slowly fill the bowl with water, trying to be very gentle, just to barely submerge this needle. There. Now the needle is touching the water, but we gotta make sure it's submerged, so I'm gonna just poke it. Okay. We have to make sure the needle is actually submerged in the water, because if not, all we're measuring is the attraction force between the needle and the water. We need to make sure we're measuring the surface tension. So let this experiment begin. Okay, there we go. This experiment took about 9 drops. This is not the first time I ran it. On average, it takes about 8 to 9 drops, so it's about right. As you can see, the needle popped right out of the water and the basket fell. The whole purpose of this experiment is to try and estimate how much force it takes for the needle to break through the water-air boundary, as shown before, and pop right out. So to begin, we need to quantify how much mass is in each drop in the dropper. To do this, I used a NyQuil measuring dose cup, and I kept putting drops from the same dropper until I got to the 15 ml mark when the meniscus hits this little 9 here. And then I just did a small division, so I got 275 drops per 15 mils, and ended up with a 0.0545 grams per drop value using the density of water to convert in between. Now that we have grams per drop, I can calculate the force using the gravitational constant and Newton's second law, F is equal to ma. Simple formula, I put in my grams per drop here, number of drops, conversion to kilograms, and the gravitational constant. This gives me about 0.005 newtons with 9 drops from my experiment. Now that we have the force, this is where the hand waving begins. We want to estimate surface tension. Well, we know surface tension has units of newtons per meter. So if we were to simplify this and treat the needle as a single one-dimensional length and use the force it took to pull the needle out, we can guesstimate how much surface tension the water and air has in the situation. So we take the force from earlier, which we plugged in here, the length of the needle, which is about 5.5 centimeters converted to meters, and plug it in here, and we get a nice value of 0.087 Newton meters, or to compare later, 87 millinewton meters. Compared to the Wiki value, we're not that far off. Wiki says the air-water tension is about 72 millinewtons per meter, and our experiment says 87. So very briefly, I'd like to outline 3 sources of error that may be present in my system. The first source of error is the biggest one. It is our assumption the needle is a one-dimensional object. It isn't, but since it's a long needle, that is very long in one dimension and very thin in the others, we can treat it as such. The second source of error can be this hinge right here. It can provide friction, which would mean we are overestimating the force needed to move this thing up out of the water. The third source would be our dropper. Since there are discretized drop sizes, we can't do half or quarter drops. So we are overestimating on that as well. I hope you enjoyed my experiment, and I look forward to seeing you all in class. Thank you.